Hi, everyone. I'm Mark Sarousu, a PhD candidate at the University of Cambridge, UK, and I'm from Ghana. I'm going to present on the title, Can Meningitis A be eliminated in Ghana? So this is part of my PhD, which looks at the epidemiology and control of meningitis in Ghana. Okay, so what is meningitis? So meningitis is an infection of the brain and the spinal cord, and the African meningitis belt, that is an area which is no pointer. Okay, so that as highlighted in the green zone, that's experiences the highest disease burden across the globe, and it has case fatality rate of 10%, and 1 out of 4 of its those who suffer from meningitis suffer from sequelae, including brain impairment and hearing loss. So even as I mentioned earlier, that this African meningitis belt suffers from the highest disease burden, though meningitis is something that is global. And this was before 2010, the highest, the most predominant cause of meningitis was due to serogroup A. And we had a vaccine in 2010 in the meningitis belt. So due to the impact of this vaccine, which is called Menafrevac, the case of serogroup A has been drastically reduced. So since 2017, there has been no case of Men A in Ghana. But for enhanced plans to fight meningitis, cases due to other serogroups, so including CWXY, still remain a public health concern. And based on this, the WHO has come with a roadmap. And in that roadmap, it is featured defeating meningitis. So as part of this roadmap, the key question, or it has come with a vaccine that protects against not only serogroup A, but also for other serogroups. So multivariant vaccine has been launched and it's on preparation to be introduced in the meningitis belt. But the key question there was, which age group do you have to target to for this multivariant vaccine? So then I started by looking at the potential vaccine scenario, so which interventions will be very realistic and feasible in trying to bring cases of meningitis down in Ghana. So I used the statistic model in doing that, and that resulted that the 1 to 19 age group, if you target the 1 to 19 age group as a catch-up for this multivariant vaccine, it will offer a good protection against the other serogroups, at the same time offering a booster against the serogroup A that had already been targeted. So, and interestingly, my results was consistent with the recommendation of SAGE. So SAGE also is a strategic group of experts on immunization from the WHO. So they also recommended the catch-up for the MMCVs, the age to be 1 to 19, and then also include the routine immunization as part of that. So the interesting thing is, though the statistic model that I used answered the intended question, so that is which age group to be targeted. But it also comes with something interesting. That is, it offers a long honeymoon period, so a period where we have low level of cases. And indeed, within this low level of cases period, we can even experience less than 1 carrier in the population. And it is interesting to see that as a limitation of the deterministic model. So always they reserve a fraction of the population. So then that also came with this new idea that can we try to explore the possibility for eliminating Men A, given the low level of cases that we are experiencing, using a stochastic model. So then what I did was I used the deterministic model that I used to investigate the age group target question. So if you look at the model structure, the top row, we have, based on the epidemiology of meningitis, we have the susceptible class, the carrier class, those who are infected with meningitis, and then those who have recovered from meningitis. And then at the bottom row are the corresponding vaccinated compartments. So individuals it is interesting to see that those in the eye, so we don't see we don't see arrow coming to the vaccinated eye. And the rationale is those in the eye have already got meningitis. So they are rather targeted for treatment rather than for vaccination. So the key features of this model is that it includes this important feature. That's the possibility of these external infections. So Ghana, even as we saw from the map, is not isolated from the neighboring countries. And these neighboring countries are also within the meningitis belt, including Burkina Faso, which is an epicenter of meningitis. So then the question is, if we are targeting to eliminate meningitis in Ghana, and given that these borders are also porous, so there's that possibility that we can also have cases from the neighboring countries. So then we try to factor that into this and see how this also impacts the elimination target. And for the purpose of this work, we define elimination to be 5 years after following the MMCV's introduction. So, and this is planned to be introduced in 2025. So after 5 years, and if you have 0 cases after 5 years, that's how we define the elimination. And because we don't have a good data in regards to people's movement across the borders, then we try to look at different scenarios to cater for that. So for the scenarios, for simplicity, I would spend time to explain it because that forms the rest of the presentation. So for scenario A, if you look at that row-wise, so the first one is we assume that Ghana does nothing. So Ghana assumed that, okay, now it's already like complacent that the cases, now we don't have any case, so everything is fine. So if Ghana does nothing and the neighboring countries also do not do anything, so this external force infection is attached to the neighboring countries. So if they don't do anything, then we don't expect that the rate at which people will move from these external countries into Ghana or infect the Ghanaians from the external sources, there wouldn't be any change in that because there is no vaccination in that sense. And then scenario B is where Ghana does nothing, but these neighboring countries also do implement this. And based on the work that was done by Dage and his colleagues, we saw that the vaccine is very effective, and that can account for 90% decline in the external force of infection. So that is why we see there. And then the scenario C is when Ghana introduces that, but the neighboring countries do not do anything. So there is no change in the external force of infection. And then scenario D is where Ghana introduced that and neighboring countries also introduced that. But you see the 40%, we assume that if the vaccine only confers only direct protection, so there is no head effect. So that 40% is the target population for these neighboring countries that we look at. And then the scenario D is where both Ghana and the neighboring countries all partake in this MMC. They implement it as recommended by SAGE. And then because of that, there's a 90% reduction in the external force of infection. So what happens with regards to that? So I show a panel of the results under each of these scenarios. So the simulation that is each of these scenarios. And under each of these scenarios, I considered different about 300 stochastic different runs. So the blue ones are the dynamics of each of the runs, and then the black one is for the average for each of the for each of all the scenarios. So we can see that for scenario A, because Ghana does nothing, and the neighboring countries also don't do anything. So cases from 1990 to 2010, we first try to consider before vaccination, within vaccination, and then following vaccination, what happens. So from 1990 to 2010, for each of these scenarios is when there is no vaccination. And following the 2012 vaccination in Ghana, that is what continues. So in scenario A, we see that following vaccination, there is it doesn't really take long as compared to the scenarios where Ghana introduced the MMCVs and then the neighboring countries also introduced the MMCV. We have a long honeymoon period, a period where we have low level of cases in that. But this one, we don't see it well. So then I zoom into I'm interested in the possibility of elimination. So therefore, under each of these scenarios, I calculated the number of simulations that die out, and then compare that to the total number of runs in each of these scenarios. So for this figure, the red one is showing a situation where Ghana does nothing and the neighboring countries also don't do anything. So in that case, there is less than 1% chance of getting an A eliminated. But if you consider, for example, the scenario, the green one, the deep green one, this is where Ghana introduced the MMCVs and then neighboring countries also introduced the MMCVs. And in that, we see a very high chance of elimination. And the one that is following this where Ghana introduced the MMCVs and then the neighboring countries also introduced the MMCVs, the light green one. But there is a 40, if we assume that the vaccine only has a direct protection against the neighboring countries, that also gives a very high chance of elimination. So what are we saying from here? So what the summary of this is, there is a higher chance of elimination if Ghana introduces the MMCV and the neighboring countries also introduce the MMCV, as recommended by SAGE group. And also, with no additional vaccine intervention, even as we can see from the option that is to my far left, there is a very low chance of MNA elimination. So the interpretation of this result is there is the SAGE recommendation offers a very good protection against MNA, but that is not all. It even goes beyond that. Based on this result, if Ghana and the neighboring countries introduce the MMCVs as recommended by SAGE, there's that potential for eliminating MNA in across the belt. However, that is not something that Ghana cannot only say that I will do my part, and the neighboring countries also say, okay, they will just not partake in this. If Ghana implements this and the neighboring countries don't do, there's a very low chance of elimination. And more to the point, if none of these countries also do anything, there's a very low chance of eliminating MNA in Ghana. Sorry. So for to study the dynamics of MNA in Ghana and even across the belt. And then also accounting for the external force of infection adds a necessary complexity for us to really understand that it's not only about just trying to look at what is happening within the local level, but what if the effects of other the neighboring countries also come into play? So what happens? So that helps us in trying to understand it from that perspective. But the key limitation for this work is due to the lack in data in regards to people's movement across the borders. We couldn't get to that. So what we did was to compensate for this. We tried to look at different scenarios to account for that. Yes, I thank my supervisor and the postdoc in our team and my university for their support so far. Thank you very much for your attention. I'm happy for questions.
Any questions? Also, I'll get to you, Kurt. Just to note for anyone online, if you have questions, put them in the chat and we'll speak them out loud to the room.
Thank you very much. That was an excellent talk. I have a question, I guess, about the baseline force of infection for MenA. I'm not familiar as much with MenA as, say, measles or rubella, but I know it's this question about a catch-up campaign in the age range for the intervention is always a question that comes up, especially because the larger age ranges tend to be more intensive, more costly. And so the question becomes like, what is the size of the age range? But there's also this acute lack of data where SARA surveys would be great, but those are also quite expensive, and informing by age of infection from surveillance data would be valuable, but surveillance can be limited as well. So I was curious, how did you estimate kind of the baseline force of infection for MenA transmission in Ghana? Thank you.
Okay. That's a very good question. So meningitis is known to be age specific. So the highest of the age burden is within the 1 to 29 age group. And therefore, and the key thing behind that is those individuals have lots of contact rates and that. So in this, even as you mentioned, so I considered an age-structured model. So for the deterministic and then the stochastic, in all both situations, I considered an age-structured model which where these individuals within the highest age group have higher contact level, differentiating that from the individuals in older ages. Yeah, so that is the rationale. So it is based on that, and then also one key thing is it's about the invasion rate. So this invasion rate, these are studies that have been done, and so build up on these results. Those are where I saw the information. So it isn't that I did the parameter estimation, but these are things that have been done, and I sourced those information from there. Yeah.
Maybe I missed it, but what level of vaccination is needed to go to cause extinction? So 10% of the population, 5%, 90%. You had the vaccine efficacy impacting transmission, but I didn't see how many people are vaccinated and how is that kind of would impact perhaps the model predictions.
Yeah, that's a very good question. So that takes us to back to the work about the age group targets. Mm-hmm. So in that, I try to look at different scenarios. So like if you target 1 to 14-year-olds in the population, or if you target 1 to 19 or 1 to 29. And the MENAFRIVAC, the one that we had in 2012, it targeted the 1 to 29 age group. 100%? The coverage rate was 98%. 98%? Yes. So with that assumption, yeah, Ghana has that culture where people really understand the need for vaccination. So there's that high coverage level. So it's the same assumption that we made for this work. Yeah.